Hey guys, welcome to another lecture for linear algebra. Today I will continue with what I had set up in the previous lecture. I was talking about the elementary row operations. What are elementary row operations? As I gave you a gist of it, basically there are three elementary row operations. One is multiplying a row by a non-zero constant, which we can also call rescaling. The next one, add or subtract a multiple of one row to another. So this would be rescaling and adding. Adding, subtracting goes hand in hand. Interchange or swapping the rows. Okay. With these elementary row operations, you can reduce, as we call it, you can reduce the rows or you can create another matrix from the given matrix. Let's take an example. How? The example that we started off with was where we had 1, 2, 4, 7, 3, 7, 2, minus 11, 2, 3, 3, 1 as our rows. And basically, it was coming from a set of equations that I had taken up. Let's take up this augmented system. Why do we take augmented system when we are working with linear equations? So that we have the left-hand side and the right-hand side together. We are working whenever we are putting any operation, whatever we are doing to left-hand side, we are doing the same thing on the right-hand side as well. Otherwise, we will lose the meaning of equation out there. Okay. Now, what is our target? When we say we want to use the row operations, elementary row operations, what do we actually want to achieve? The basic idea is that we want to create zeros in order to simplify this set of equations or this matrix. So what we try to do is we try to create zero below the main diagonal. Suppose I tell you that use the first row in order to create zeros in the first column of the second and third row. What will you do? Pretty easy. I would multiply the first row by 3 and subtract that row from row 2 and I will be able to create a 0 here. Similarly, I'll multiply the row 1 with 2 and then subtract from row 3 and I will get a 0 here. These are the row operations we are doing. The one that I said, rescale, add, subtract, that's what it is. So we say R2 goes to R2 minus 3 times R1, R3 goes to R3 minus 2 times R1. And that, my friends, will give you 3 minus 3 here, 2 minus 2 here. But along with it, of course, the rest of the row will also change because you're using the operation on the entire row. Okay. So 7 minus 3 into 2 is 6. So 7 minus 6, 2 minus 3 into 4 is 12. So minus 12. Minus 11 minus 3 into 7 is 21. So minus 11 minus 21. Similarly here, and this will give you the following matrix. So see, you have been able to create zeros here. But what did I say? I want zeros below this main diagonal. I want zeros below this main diagonal. So that means I don't want to see minus 1 here. I want to see 0 here. So what if I tell you that use the second row to make a 0 here? In the second row, first element is 0. So if I use the second row, it will not touch the 0 that has already been created in row 3. The first entry here, right? 0 plus 0, 0 minus 0, we'll always let it be just 0, right? But here, if I just add up this 1 to this minus 1, it will become 0. I should change R3 by adding R2 to R3. So what will happen? I'm adding R2 to R3 and that, my friends, will give me a 0 here. But of course, it will make some changes here as well. So minus 5, minus 10, minus 13, minus 32. And this in turn will give me a matrix that looks like this. Now in this matrix, what has happened is that I have zeros here. Now ask yourself why we must have done this. For a very simple reason that now it will be very easy for me to visualize the system of equations and find out the value of the variables. So if you start rewriting these as set of equations, you will get, look at the last row, okay? From the last row, what do you get? 0 into x plus 0 into y minus 15 into z is equal to minus 45. So that gives me minus 15z equals to minus 45, which gives you z is equal to 45. So z is equal to 3. Isn't this what we actually got prior to this method when we figured out in the previous lecture? Yes, we got z from here. And from the second row, what do I get? From the second row, it's 0 into x plus 1 into y minus 10 into z is equal to minus 32. And hence what I get is that y minus 10 times z is equal to minus 32. So y is equal to minus 32 plus 10 times z. Z value we already have, so this becomes minus 32 plus 30, and that gives me minus 2. This is what we got earlier as well. Now, let's write down the first row as an equation. So the first row as an equation gives me x plus 2y plus 4z is equal to 7, which was our first equation. So writing that down, I have the value of y, I have the value of z. It's easy for me to find the value of x. And x will be 7 minus 2y minus 4z. Hence that becomes 7 minus 2 into minus 2 minus 4 into 3. And that is 7 minus minus plus 4 minus 12. That's 11 minus 12. That's minus 1. So the answer that we get is minus 1 out here. Of course, the answer is same as we got with the previous method. Observe what we did in this process. We just transformed the given system to another system. So we had certain equations given to us. We used the row operations, elementary row operations, and we got new equations. The new equations were this one, and this equation. Now, all we have done is, by using row operations, we have transformed the given system of equation. The only reason why we use row operations is that it simplifies the process. And the chances of making mistakes are reduced when you have too many variables to take care of. This process is called the Gaussian elimination process. Another thing, when you use the elementary row operations on a particular matrix, you achieve another matrix by using these three operations. These two matrices will be called row equivalent. The two matrices are called row equivalent to each other if one matrix is derived from the other by using these three elementary row operations. Let's work on another system of equation to be sure of what we are learning. Step number 1, what will you do? You will create the matrix, augmented matrix. 1, 4, 5 for x, 3, 4, 1 for y, 2, minus 3, 2 for z. And your right-hand side out here. Now you have to use these three elementary row operations in order to create zeros, as I mentioned in the previous example. So we will be using our row operations. Number 1 will be R2 goes to R2 minus 4 times R1. R3 goes to R3 minus 5 times R1, because that will give me a 0 here and a 0 here. This is the matrix that you will achieve after using these two row operations. Now, what is our task? Our task should be to create another 0. I don't want this to be minus 14. I want this to be 0. How can I do that? This time it's not as straightforward as it was in the previous question. So you have minus 8 out here. Use the operation R3 goes to R3 minus 14 by 8 R2. In the process of doing that, what will happen? If you do 14 by 8 here, minus 8 will turn into, cancel out with the 8 in the denominator, and 14 will be left. And then since it's minus, so what you require is, you actually would require positive here. That's why minus here. And this in process will give you 1, 3, 2, 13 as it is, 0. Now here you have minus 8, minus 11, minus 49 as it is. Here you will still have 0 because this operation will not make any difference to this 0. So after using the operation, here you will have minus 14 plus 14. Here you will have minus 8, minus 14 by 8 into minus 11. Here minus 52, minus 14 by 8 into minus 49. Which means the matrix will turn into 1, 3, 2, 13, 0, minus 8, minus 11, minus 49, 0, 0, 45 upon 4, 135 upon 4. Now, the concept that we just learned about row equivalence. This was the original matrix that you started off with. You used the elementary row operations, the basic three operations, nothing beyond it. And you were able to achieve this matrix. These are row equivalent matrices. Now, what you will be doing, because what are we interested in? We are interested in the value of x, y, z that would satisfy this system of equation. So from here, what I get, the last row could be represented as equation 45 upon 4 times z is equal to 135 upon 4. That means z is equal to 135 upon 45 equals to 3. Z equals to 3. Now, with the back substitution, you can get minus 8 y minus 11z is equal to minus 49. From the second row, this is what you're getting, right? So minus 8y is equal to minus 49 plus 11z. That means minus 49 plus 11 into 3. That is 33. Minus 49 plus 33 is equal to minus 16, which gives you minus 8y is equal to minus 16 implies y equals to 2. Now, from the first equation, you will get x plus 3y plus 2z equals to 13. And that implies x is equal to 1, which means in this situation, we are getting a unique solution just like we were getting in the previous example. Just observe what has happened. By using the elementary row operations, this was my original system of equation. It changed into this system. What we have done is this triangle, can you see? This triangle area, we made zeros out here. The coefficients turned 0, so we were able to convert this system. Both these systems have the same solution set. That is the benefit of Gaussian elimination, okay? And that's the reason. The only reason why we use Gaussian is to get rid of the mistakes that we could have made, and it is just to simplify the system of equations. This is a very good method in order to find out solutions. Now, what you need to remember is when you use the row operations, the Gaussian row operations or the elementary row operations, the two systems which are row equivalent, okay, these systems, these are equivalent systems, they have the same solution set. Let me quickly also tell you about something else. What if I want to convert it to 1? All I will have to do is that multiply this row by 4 by 45 and I'll be able to do that, right? So let's use another operation. R3 goes to 4 upon 45 times of R3. Yes, you are rescaling, okay? Hence you get the same matrix. Everything remains the same except for you'll have a 1 here and a 3 here. Now do you see what has just happened? The moment you will look into this matrix, you will be able to say that z should be equal to 3. That's the benefit of this method. In fact, if we use some more operations, we will be able to reduce this matrix to 1, 0, 0, 0, 1, 0, 0, 0, 1 with something here, something here, something here. There will be some, changes, of course, in the right-hand side because you will be using row operations. Use your row operations, reduce this matrix to this kind of a matrix. Do you see what will happen here? I will be directly able to tell what is the value of z, what is the value of y, what is the value of x. Actually, whatever we got as x, y, z, if I just put that in my right-hand side, that would be correct. Because whatever operations you will use, you are getting a unique solution, which you already figured out, x, y, z, right? So this is called reduced row echelon form. If you reduce your system of equations to a reduced row echelon form, you will be able to directly get the answer. In fact, this will be our point of discussion in the next video. So I'll be teaching you what is row echelon form, what is reduced row echelon form. See you in the next video.